For our next example, what I want us to do is consider we got these two metal plates right here. So we get a metal plate, the upper one is positive, lower one is negative, and let's say the two metal plates have an established electric field between them, and the electric field is 6750 newtons per coulomb. So we have an electric field in here, like that. Now, let's also say I'm going to put a little charged particle in here. So this charged particle there, that charged particle, I'm going to say, has a mass of 65.5 grams, and Q is unknown. And that's what I want us to calculate. What is Q? What's the charge here that balances this? Okay, so that's what we got. So we want to find Q. Well, it's balanced, therefore it's an equilibrium. So we know from physics 1, the equilibrium, free body diagram, we got mg pulling down, so there has to be a force upwards here. That's going to be the electric force. So the electric force has to be equal to mg. Now, you very quickly realize, F equals QE, and so that means that QE equals mg, so Q equals mg over E, and you start solving the problem. But, warning, before we do that, let's take a moment to think. Yeah. And this is where it's important to solve the problem correctly. Remember what we got here. We've got this charged particle floating in here. We got the electric field pushing down, but the force has to go upwards. From free body diagram, it has to balance gravity, so the force has to go upwards. So F equals QE, yes, but this is really a vector sort of thing here. So what that means is that since the E vector is down, the F vector is up, that implies that Q has to be negative. So it has to be less than 0. So the Q must be negative here in order for this to work. Okay, so that means that the equation that we just derived, in which we said that Q was mg over E, we need to have a minus sign in there, okay, because we need this to be negative. Now, this is where it is very important to actually draw the picture. In Physics 1, I tell my students, draw the picture. Why do you draw the picture? Why do you label things on the picture? It takes up extra space. It takes up extra paper in your homework. Deal with it. It is good for you, because when you look at something, your brain visually processes it. You're using a different part of your brain than the part that's analytically processing. Okay, so this is a difficult subject. You're actually more likely to get the answer right if you use your whole brain, not just half your brain. And so don't just do this half-brained. Do it whole-brained. Draw the picture, involve the other part of your brain in looking at the problem. I often tell people it's not a bad idea here to draw this, to label things. Now the way that I'm doing this right here, I only have one easily available color here, but I would actually use different colors to draw it, so that if I were drawing it on homework or something, I would draw everything different colors so that it's obvious when you look at it what the situation is. And so I would draw the electric fields one color, the charges a different color, and the forces a different color, etc. Just get used to using lots of colored pencils, and that would help. Okay, it takes a couple extra seconds to do this, but it saves a little bit in terms of thinking about it, and you're more likely to get a good grade if you use your whole brain. It actually makes it easier to solve the problem. Believe it or not, it actually makes it easier. So I would recommend definitely doing that. So Q minus, okay, the mass was 12.3 grams, so that's 0.0123 kilograms, G 9.81 meter per second squared, and then E, that was 6750 newtons per coulomb. So Q comes out to be a negative 1.78 times 10 to the minus 5 coulombs, or you could write that as minus 17.8 microcoulombs. Obviously, I would take either one of those because they're both actually correct. Okay, my next question about this problem, so that's like part A of the problem was, what's the charge on it? B, how many electrons were added or removed to give you the charge? Okay. So if you want to find the number of electrons, then that's going to be the charge divided by fundamental charge. Okay. And so I'm going to just take absolute value here. Okay. So that would be 1.78 times 10 to the minus 5th coulombs divided by 1.602 times 10 to the minus 19 coulombs. And so that comes out to be 1.12 times 10 to the 14th. Okay, now we know that the charge was negative, so this was negative. So that means that we added these electrons to it. So we added 1.12 times 10 to the 10 to the 14 electrons. Okay. Now, we're adding electrons to this thing. So that means that we're also adding mass to it. So the question is, how much did we change the mass by adding these electrons? So we have a question. How much did we change the mass? So we added all these electrons. So what was the change in mass? How do we do that? Well, we just look at the mass of the electrons. So the change in mass is going to be mass of electrons times the number of electrons. Well, you look up the mass of an electron, that's 9.11 times 10 to the minus 31 kilograms. And then you take that and you multiply that by the 1.12 times 10 to the 14, which is the number of them that we added. So the change in mass is 1.02 times 10 to the minus 16 kilograms. So we increase the mass by this amount. Now, why is that not negative? Well, because we added electrons. Adding electrons means we increase the mass. If that was a positive charge, then that means we took electrons off of it, and so this would have been a negative change in mass. So in order to make something a positive charge, you're normally removing electrons and decreasing the mass. If you're trying to make it a negative charge, you're adding electrons and increasing the mass.